Hi everyone, welcome into the November webinar. This is Stacy and we're here with my colleague Soha, and we're going to be sharing some information with you today relating to excipients used for viscosity reduction in biological materials. And we've talked about these sort of independently in the past, where we would address certain types of biological materials and the types of excipients that would work with them. But we're kind of going to bring them together today to get a sort of a broad overview. And specifically, we're going to sort of contrast how excipients work when you're dealing with something like DNA in solution versus a protein or an antibody in solution. So that's sort of the topic today. So let me get started with just a quick review on what is an excipient. So most of you who are joining in are probably familiar with this. And the excipient is going to be some non-active component that you include in the formulation. And it's really intended to control specific properties, generally physical properties. So one common desire when you include the excipient is to be a rheology modifier, more specifically to reduce the viscosity. Another benefit that is often desirable when you include these is to enhance the stability of your formulation. And this could be for storage, so aging stability or thermal stability. Now, they're necessary, these excipients or these non-active components are necessary in biological materials because of the inherent interactions that exist between the proteins or the antibodies and also with the DNA. And we'll talk a little bit more about that shortly when we start to sort of compare and contrast them. And these interactions lead to a particular microstructure in the solution. So microstructure is just what is the spatial rearrangement of either the antibodies or the DNA in the solution. And because of these interactions and because of the structuring that occurs due to them, oftentimes what we'll see is the viscosity as, say, a function of concentration can increase very rapidly. And so that can be impractical, and the introduction of these excipients then can be necessary. So most often the excipients are going to be small molecules, and by that I mean something with a molecular weight so that it would not be classified as a polymer. And the excipient will be specific to the particular active in your formulation. So we're talking today about antibodies protein type formulations in comparison to formulations with DNA. And these molecules, depending on which active they're meant to work with, will have a different type of mechanism and introduce or induce different structural changes. So let's now make a comparison here between antibodies and DNA, just so we can sort of understand what's different about them and why you need different excipients to control things such as viscosity and stability. So if we look at, let's first look at sort of sizing of these molecules, these biological macromolecules in solution. So antibodies are proteins. They tend to have, depending on whether it's a globular protein or more an antibody type structure, and our image here over to the left is more how we view the antibodies. They tend to have a molecular weight somewhere between about 66 and 150 kilodaltons. Now, DNA, the molecular weight can vary quite a bit, but we're just going to sort of share what our experience was using calf thymus DNA, and that was that these tended to be more, or that you had the potential to have significantly higher molecular weights here. So the base pair molecular weight is 650 daltons, and then depending on what number of base pairs you have in your particular DNA sample, you can have typically in excess of 1 million daltons. And so when Soha, who will overview our data collected with DNA, discusses this, that particular DNA sample was, we estimated to be slightly above 3 million. So these molecules are very different in size. And in addition to that, they have a different type of what I'm sort of referring to as primary unit structure. So how can we describe the nature of the individual molecule is what I mean by that. And with the antibodies and proteins, they tend to be more viewed as a colloidal system or a colloid. And this is because there tend to be sort of fewer degrees of freedom with the proteins and the antibodies such that they won't extend out as polymers do, so they're not going to overlap and entangle in the same way. Their structure is more fixed. due to the higher order structures that exist here, such as the single helix and then the sheet folding. They tend to be more fixed and tend to more consistently occupy, say, a spherical volume in the solution. So they tend to be more considered as a colloidal type material. And also consistent with the sort of colloidal framework is the idea of the interaction potential between the different proteins or antibodies. And they tend to have, both types of interactions, both repulsions, most commonly from electrostatics or charge, and then they also have attractive sites. So they tend to have a mixed type of interaction, having some electrostatic repulsion, which can act as a stabilizing barrier, and then attractive sites, predominantly perhaps from hydrophobic domains that exist on the structure. The DNA, on the other hand, tends to form consistently this double helix. So you'll have two strands of the DNA where you have hydrogen bonding between the base pairs, forming this double helix structure. And it's anionic, so it's charged. And so the general view in many instances is that this is almost like a polyelectrolyte with a stiff backbone, so that you end up having some sort of extended worm-like or coiled structure. So extended due to the stiff nature of this double helix, and also extended due to the fact that it's negatively charged, which gives you intramolecular electrostatic repulsions. So with that in mind, given the fact that these antibodies are more compact, they're more considered colloidal, they tend to have a solution microstructure where you have, in some instances, you'll have a decent number of primary or individual molecules, but due to the inherent nature of the attractive sites, they tend to aggregate or form clusters. And this is also consistent with how colloidal systems with attractive interactions behave. So they tend to form different size clusters depending on the exact nature of that stabilizing barrier and the magnitude of the attraction. Whereas because of the DNA being a significantly larger molecule, more extended due to that stiff charged backbone, at higher concentrations, you can get something that's going to overlap or entangle. So we have two very different systems here based on the type of biological macromolecule we're dealing with. So that means when you come in with an excipient and you're trying to choose the excipient, it's going to function differently, which means you're going to need a different type of excipient. So if the goal then is to, as we said in the intro there, was to reduce the viscosity and then also enhance stability, then what you're really going to want to do with these antibodies or proteins, which are more of a colloidal type material, is minimize these attractions and therefore minimize the aggregation or the cluster size. And that's going to be your mechanism to achieving reduced viscosity and enhanced stability. However, with the DNA, again, reminding you that we have something that's more expanded, more prone to overlapping or entanglement as you increase concentration. In this instance, oftentimes the excipient, particularly related to the viscosity modification, is referred to as a condensing agent because it's actually acting to collapse or create a more compact structure, which is going to then minimize the overlap and entanglement and then reduce the viscosity. And Soha will talk more about that when she gets to that section of our talk. She'll discuss certain types of structures that you may induce when you introduce these condensing agents. So with that in mind, excuse me. Sorry, I need some water. So with that in mind, we're going to need different types of excipients depending on the biological material that we have. So some very common ones that are used in antibodies and proteins are individual amino acids, sugars. Sugars are most typically used when dealing with or considering them as a cryoprotectant, surfactants, and then various salts. Whereas with the DNA, you really need multivalent cations, something with a valence of 3 or greater. And then also you can use water solvent mixtures, most commonly water alcohol mixtures. And again, kind of making the analogy to DNA being more of a charged polymer type system, the goal with the water solvent mixtures or the water alcohol mixtures is to really cause a shift in the solvent quality, which again is going to lead to a collapse of the structure. So with that in mind, I'm going to jump into the antibodies and protein type excipients before Soha then will finish it off with those for the DNA. So just to get an overview of what we're going to share when it comes to the protein data, we're going to look at model protein data. So we had bovine gamma globulin, or BGG, and we introduced two main classes of the excipients because they, depending on, what, which particular literature you look at, they seem to act in a slightly different way potentially. So we're going to look at introducing different types of salts and also introducing individual amino acids. Some of the most common ones are arginine and histidine. And we're going to use, to do our viscosity measurements, we're going to use our Vrock Initium 1+. And just to sort of get it out of the way and to also share some of our technology with some of our participants in the webinar that may be new to RioSense, I'm just going to quickly review our instrumentation prior to jumping into the data. So our core technology is what we refer to as Vrock, which is viscometer rheometer on a chip. And this is a combination of microfluidics and microelectromechanical sensors, or MEMS. So more specifically, we create a well-defined microfluidic flow channel, which has along the base of the flow channel spaced out pressure sensors. And so we control the flow through the flow channel, which allows us to control the flow rate, or sorry, the shear rate. So we're controlling flow rate Q, which allows us to calculate a shear rate using that flow rate and the geometry of the channel. And then we measure the pressure drop across the base of the channel, which would look something like this, pressure as a function of sensor positions. And then we use the slope from this pressure drop across the channel along again with the dimensions of the flow channel to calculate the shear stress. And with this, then we can calculate shear stress proportionality to shear rate, gives us the dynamic viscosity. So that's the core of our technology. So, and this is across the board in all of our instrumentation. We, however, for the data we're presenting here, we're using our Vrock Initium 1+, which is our automated system, and really ideal for biological materials because you can get away with using very small volumes due to some of the features here. So this is just sort of a bird's eye view of the system. And the way this works is the auto sampler will inject your sample into the test syringe, and then we will force flow through the test syringe and then into our chip. And inside the chip is housed that microfluidic channel that I just had a cartoon of on the previous slide. And because this system is closed, we don't have to worry about any interfacial effects on the viscosity. So that would include evaporation as well as any migration of the components such as the antibodies through the interface. Sorry, I'm just pausing here for a second. I thought I saw okay. Sorry about that. I thought I saw a hand going up on the chat. I was concerned that maybe our sound wasn't good, but okay. So back getting at it here. So so we don't have the interface, so you don't have to worry about migration to the interface or evaporation, which is important in general for the proteins, antibodies, and biological materials, but also important when you're doing temperature variation and increasing the temperature, which some of our data today that we're presenting was collected at an elevated temperature. Okay, so that's our technology that we use to generate all of our data today. So let me start off with talking about salts as an excipient and a means of controlling viscosity. And before I get into the data with the specific salts at the various levels that we used, I wanted to talk about what's referred to as the Hofmeister Series, because this Hofmeister Series can kind of guide you in selecting your salt for whatever purpose you may have, and also sort of interpreting the data that may come about afterwards. So they tend to be put on this spectrum here, both the anions and the cations, although the anions tend to have more influence over the behavior of the proteins and antibodies when you include these into solution, but they both have a spectrum, and we'll focus on the anions because they are more significant. And on one end, you have something that is more strongly hydrated, and on the other end, it's more weakly hydrated. So what that means is when you put the salt in solution and it dissociates, you're going to have a certain amount of, or a certain level of water molecules that will associate with the cations and anions. And so weakly hydrating just means that these ions in solution, when dissociated, are not going to, have a very tight or close layer of water molecules, whereas the strongly hydrated ones will have a strongly or a larger shell of water molecules. And the importance of that is that, the thought is that the influence of these salts are going to impact the surface hydration of the protein, and that this is really what's going to drive the behavior in the presence of the salts. So the idea is that these weakly hydrated salts, so this is something down on this end of the spectrum, and so in our case, our experiments, the sodium bromide that we use is sort of more on that end of the spectrum, tend to be better at salting in, is the language that's used, because these molecules, such as the sodium bromide, aren't going to have a strong hydrated layer, so they're going to allow water available to hydrate the surface of the protein. And this will then, theoretically allow that protein or prevent that protein from becoming dehydrating and aggregating. And so on the flip side then, if you go to the other end of the spectrum, so something like a sodium sulfate, these strongly hydrated salts, which are potentially going to pull water away from the protein, are better at salting out. So that's kind of the general idea of the behavior of the salts and how they might impact the nature of the protein once they're in the solution. So what does that mean then in terms of the data when you collect viscosity data? So we're going to look at the low shear plateau viscosity as a function of ionic strength. And again, as I mentioned, we're looking at our model protein, bovine gamma globulin, or BGG, at a high concentration, so 250 mg per mil. And just to the low shear plateau, so this is the Newtonian plateau before the onset of shear thinning. Because if you are familiar with doing shear rate sweeps on proteins or antibodies, they tend to be, at least in the concentrated state, non-Newtonian with a plateau in the lower shear rate range. So we're just looking at that plateau value. And so we have that here on the y-axis as a function of ionic strength in units of millimolar. And as I mentioned before, we're looking at different types of salt and then at these different levels. And we actually then also looked at it at two different pHs, one where we're close to the isoelectric point, so we're expecting to have little to no charge there, and one where we're above the isoelectric point, so we're expecting that to be anionic or negatively charged. And so what we can see in either instance with these salts is that we have some initial period where we see the salting in. So presumably then we're seeing an increase in the hydration of the protein with the presence of the salt, which is going to enhance the solubility. And, in the same, at the same time, decreasing the attraction and decreasing the viscosity. However, if we continue to add salt, we bump up the ionic strength, then we see a minimum and then an increase. And the increase, of course, will depend on which salt we're using. And the minimum point will depend on the salt that we're using. But presumably then we're entering into this salting out phase, where now we're decreasing the hydration of the proteins and then decreasing the solubility, and therefore increasing attraction or increasing viscosity. And we do see a difference between the two different pH values, depending the main factor there being that changing the pH changes the level of charge or the electrostatic repulsion between the proteins. So presumably this change in behavior with the salt comes from the fact that as we move away from the isoelectric point, comes from the fact that these salts can also screen electrostatics. So we're impacting not only the hydration of the molecules and therefore sort of enhanced attractions that might occur when they're dehydrated, but we're also sort of modulating the electrostatic repulsion. And we can see here from the data that, we're kind of getting what we might expect based on the Hofmeister series. And so by that, I mean, in terms of being most beneficial in terms of salting in, that would be the sodium bromide. So if we look at either of the pH values, we see that the sodium bromide has a longer salting in period and then sort of minimal salting out, and very minimal when it comes to the negatively charged particular pH there. And then the opposite case is the salting out, where we would expect the sodium sulfate to be most impactful there and sodium bromide to be least. And so we can see that, yes, sodium sulfate does in fact cause a very significant increase in comparison to the other salts as we increase the concentration. And sort of in between both of those would be the sodium chloride and potassium chloride, which, as we can see in the top plot here, are fairly similar. And I just wanted to point out that so if we take some of those data points from our previous plots, and so remember I had mentioned that we were only looking at this plateau viscosity in that particular comparison, where we were looking at so many data points from the different salts and ionic strengths. If we take some of these particular formulations where we varied the salt and that particular level of the salt, and we actually get the full profile, by that I mean viscosity as a function of shear rate, you can see the very wide range of behavior that we get for one particular concentration of the protein. So this really shows you the influence of these small molecules on how the individual bovine gamma globulin molecules interact. So all of these formulations have that same concentration, the 250 mg per mil of the gamma globulin, and we're causing this very broad shift in not only overall viscosity value, but shear thinning behavior, both onset of thinning and then the particular power law that it decreases with as we increase shear rate. So these small molecules are very powerful when it comes to controlling rheology given a fixed particular protein concentration. So let's then shift into a different type of excipient that is common to proteins and antibodies, and these would be individual amino acids. So again, we're going to focus on the low shear plateau viscosity, and again, we're going to look at a concentrated bovine gamma globulin. In this instance, we're adding 6 different excipients here, all at 125 millimolar, and we're going to compare that to the gamma globulin in our base buffer, which is detailed down here below. It's an acetate buffer. And so what we have here are histidine and arginine, both with and without hydrochloride present, HCl. And we're also going to include in the mix here basically one of the functional groups on the histidine, which is the imidazole, and then the guanidine, which is the functional group on the arginine. And we're going to see how the introduction of these at this particular level will reduce the viscosity. So depending on where you look in the literature, some people also explain the function of the individual amino acids in terms of impacting the interactions of the proteins, also related to the water issue, but then other people will explain them more in terms of that they're acting as a screening agent, both for hydrophobic interactions and electrostatic. So in that particular type of view, these molecules are basically acting to associate with, say, a hydrophobic domain on a protein, which then prevents that hydrophobic domain from interacting with one on another protein molecule, thereby sort of blocking the ability to form that attractive interaction that could lead to the clustering or aggregation. Also, because these, depending on the pH of your solution, both of these can have a charge, arginine being charged over a more broad range of pHs than the histidine, so more arginine being more influential in this way, but they also impact or suggest that they can act as, sort of like a salt would act to do the electrostatic screening. Because remember, these proteins tend to be charged, and although it is beneficial to have an electrostatic repulsion in terms of having a barrier, a stabilizing barrier, that repulsion does increase viscosity as well. So a lot of people tend to talk about these as though they're extremely beneficial because they view that they do both those things. They sort of minimize that repulsion that can increase viscosity, and then they minimize the attraction that will also increase viscosity. So what we see here then, with that long-winded explanation there, the low shear plateau viscosity as a function of this type of excipient that we've added. And again, comparing it to the buffer only, our base buffer. And so we can see that all of these do reduce the viscosity to some extent. However, we see that the most beneficial ones for this particular protein which is the BGG, tends to be the arginine, and then to the lesser extent, the arginine hydrochloride. But overall, they can all benefit in some manner. And of course, we were just looking at a single concentration here, but you can use this measurement, the low shear plateau viscosity measurement, as a screening tool to sort of both optimize both the individual amino acid that works best with your protein or antibody, and then also optimize the concentration that you will need to get the viscosity reduction that's desirable for you. Okay, so one more thing here before I pass it on to Soha. So I wanted to talk also about the thermal stability. And in some of our previous content, we've talked about sort of aging stability, but sort of in interest of time, I've picked just the thermal stability or the onset of protein denaturation as you ramp up temperature. And so let's consider, how do these amino acids help in this particular area? And for these experiments, we dropped the concentration significantly so that we didn't have any issues with our experiment in our microfluidic flow channel. If we did the same experiments with the 250 mg per mil, we would clog things up. So we need to drop it for this type of experiment. But we're going to add the individual excipients, again, the amino acids, and then the functional groups, imidazole and guanidine as well, at the same level. And so what we did was we did basically a heat-cool cycle, where we ramped it up from 35 up to about 64 and then cooled it back down. And we're looking at the top thing here, we're looking at the relative viscosity. So relative viscosity is just the protein solution viscosity scaled on the buffer viscosity at each particular temperature. And so what we can see is that initially this is just sort of flat, so we don't see any sort of change that's coming from changes in the nature of the molecules or how they're interacting until we get to a particular temperature, maybe about between 60 and 62, and then we see an increase that persists even after we cool. And then we can also see that depending on the particular formulation we have, so in this case, do we have L-arginine or L-histidine, we see that we have a difference in that irreversible change that comes from that thermal stress that we're introducing. And so what we were trying to then classify or categorize down below is, what is this irreversible change in the relative viscosity in terms of percentage as we change our formulation. And then we want to compare that to buffer alone. So this is interesting when you think about what we just looked at and how these excipients behave in the concentrated state at room temperature. Now we're seeing in some cases, or probably the majority of the cases, we see that the presence of these excipients, these amino acids, are actually making the situation worse. We do see some benefit here with the histidine and its functional group, the imidazole, where we see only a slight increase in viscosity after heating and cooling back down, better than the buffer alone. But the majority of these are actually worse than buffer only and no excipient. So it's kind of important then to get in there and do the experiments to try to understand what is happening and get the data for your specific goal when it comes to introducing the excipients. So I'll stop with the proteins there and pass it on to Soha. And so just to sort of intro her, she's going to be talking about the DNA side. And so at the very beginning here, we sort of provided the contrast on how DNA is a different beast than the proteins and antibodies. So the behavior of those and the type of excipients and the mechanism there will differ.
Thank you, Stacy. In the first part of this presentation, Stacy explained the role of excipients in changing the rheological behavior of biological molecules like proteins and antibodies. Now I'm gonna talk more about DNA, giving you some basic information about DNA structure and DNA condensation, and then share some data with you. I will show you how we use viscosity to understand the structural changes that occur in DNA molecules in the presence of excipients. One type of excipients that are added to DNA to modify their rheological properties are called condensing agents. So I want to go over some basic information to see how condensing agents can change the structure of DNA and see how viscosity measurements can reflect these changes. DNA is a negatively charged polymer that has a double helix structure composed of two single strands wound around each other that carries the genetic information of living systems or living organisms. DNA condensation refers to the process of converting elongated, negatively charged random coils into smaller, compact, or condensed molecules. This process leads to structural changes and a reduction in the effective volume of the DNA molecule. Then we would expect to see some sort of viscosity reduction. In some cases, depending on the type of condensing agents and their concentration, they can lead to precipitation of DNA. One common structure that is formed in the presence of condensing agents is toroidal shape that you can see here. And now if you zoom in on these basically concentric rings, you see that you maintain the double helix, but now it's sort of wraps around itself. So now the driving force for this process depends on the particular condensing agent you use. If you're using agents that neutralize the charge of DNA, then you're gonna reduce the electrostatic repulsion among different portions of chains that lead to the formation of condensed or compact structure. Also, if you reduce the quality of solvent, for example, by adding ethanol to DI water, the DNA molecule will collapse and form the condensed structure. So changing the solvent and not necessarily adding charge neutralization agents can also be the driving force for creating condensed or compact structure in DNA molecules. So some of the common agents that are used as DNA condensation agents are multivalent cations such as polyamine spermine, which has +4 charge. So these are charge neutralization agents that minimize electrostatic repulsion. Also, by introducing alcohol into the DI water, you will change the quality of the solvent, going from a good solvent to a more poor solvent that leads to DNA condensation. So before I show you the data I collected, I want to briefly explain the sample preparation, and after that I will share and present the viscosity data with you. In order to understand the effect of condensing agents, we prepared solutions containing DNA and condensing agent in DI water. The condensing agent we used for these experiments is called spermine. The exact condensed structure that can form in DNA molecules depends on the type of condensing agent that you use. Here we sort of highlighted the toroidal structure because it seems to be the most common structure when you introduce spermine into your DNA solution. So we prepared two different DNA concentrations, including 2 and 6 mg per ml, and then added various amounts of spermine to them. We measured the viscosity of DNA solutions containing different concentrations of spermine. We studied one shear rate that is 2700 inverse second, and temperature range from 15 to 70 degrees Celsius. What we want to learn from these experiments is to understand how condensing agents can affect DNA structure in a temperature sweep experiment. And the reason that we performed a temperature sweep experiment is to understand the thermal transition and specifically melting or denaturation of DNA samples in the presence of condensing agents. And the good thing is that the changes in DNA structure in the presence of condensing agents can be monitored with viscosity measurements. And so our Vrock initium is an ideal instrument for measuring viscosity. In this system, you need a small volume of sample to measure the viscosity at different temperature, which is important for us since DNA and many of biological samples are relatively expensive. So after this quick review of experiment and sample preparation, I'm going to go over the viscosity data I collected from our Vrock initium and share some results with you. This plot shows measured viscosities of aqueous 6 mg per ml DNA containing 100, 200, and 300 microgram per ml spermine over the extended temperature ranging from 15 to 70 degrees C. It is evident from this plot that the addition of spermine decreased the viscosity. As seen, it is more pronounced above 50 degrees C. At this point, viscosity rises steeply to a maximum, followed by a gradual decrease. However, this gradual decrease in viscosity is seen for samples without spermine and low concentration of spermine, I mean 100 microgram per ml. For the other two samples with higher concentration of spermine, which are the red and green symbols on this graph, this viscosity reduction shifted to the higher temperature, I mean temperature higher than 70 degrees C, that is out of the initium range, and we are not able to monitor that. Now let's see what happens when we start increasing temperature. As you know, in DNA structure, two single strands are bonded into one double helix, and initially the increase in temperature disrupts hydrogen bonding that leads to partial separation of double strands. So you're going to have more expanded structure, and there would be some potential crosslinks with single strands and neighbors that lead to an increase in viscosity. So this viscosity increase that you see in this plot most likely occur because of DNA melting. So at melting temperature, some of the hydrogen bonded double helix separate, I mean the hydrogen bonding disrupt partially and not entirely. So that many more crosslinks are formed than are possible, and then the adjacent molecules start to cross-link together, and this increase in cross-linking leads to an increase in viscosity, which is clear in this plot. Also, with increasing spermine concentration, melting or denaturation temperature shifts to higher temperatures. Now the question is that what happens after the viscosity maxima? The answer is that DNA melting dominates only in a limited temperature range, and at higher temperatures, the crosslinks break up due to the decrease in stability of hydrogen bonds. I mean, further heating disrupts all hydrogen bonding. So this is why we see viscosity drops at higher temperatures. With that in mind, now let's take a look at the relative viscosity data versus temperature. The plot in the left shows the same samples as the previous slide and the corresponding sigmoidal fit for each curve. Actually, we quantify DNA melting by defining the melting temperature. To define it, we take sigmoidal fit of the temperature ramp-up data. We set the midpoint of this fit as the DNA melting temperature, which is consistent to how it's defined in the literature. The plot in the right shows melting temperature as a function of spermine concentration. I think now it's clear that with increasing concentration of spermine, the melting temperature shifts to higher temperature. For example, in the sample without the spermine, the melting temperature is around 59 degrees C. However, in the 300 microgram per ml sample, melting temperature shifts to temperature around 66 degrees C. Spermine is a cationic component then when added to the DNA solution associate with negative charges on DNA structure and neutralize the charge. And so the internal electrostatic repulsion decreases, as I explained a few minutes ago. And the molecule undergoes a conformational transition to a condensed or collapsed structure and forms a toroidal shape. So the active volume fraction of DNA drops, and this is the mechanism why viscosity drops in the presence of spermine. When the solution is heated up for samples with higher concentration of spermine, more energy is required to first unfold or break up the ordered toroidal structure or overcome the condensing state, and then overcome the hydrogen bonds in the double helix structure. So this is the reason why melting temperature increases with increasing condensing agent. So we performed the same temperature sweep experiments with another concentration of DNA, which is 2 mg per ml, and 5 different concentrations of spermine. The plot in the left shows the relative viscosity as a function of temperature. These samples show the same behavior or same trend as 6 mg per ml DNA, such that increasing the concentration of spermine increases the melting temperature and reduces the viscosity. Also, the plot in the right shows melting temperature as a function of concentration of spermine, as expected and as we discussed a few minutes ago. With increasing concentration of spermine, melting temperature increases. So we also were interested to see how introducing ethanol to DI water and changing the quality of solvent affects the viscosity and melting temperature of DNA samples. So we prepared 6 mg per ml DNA samples by dissolving it in 5, 10, and 15% ethanol. We studied one shear rate and temperature range from 30 to 70 degrees C. What we want to learn from these experiments is to understand how ethanol or a solvent quality can affect DNA structure in a temperature sweep experiment, and how it can change melting temperature and viscosity in general. So just like previous experiments, with spermine, we can monitor changes in DNA structure in the presence of ethanol with viscosity measurements. So again, we use our Vrock initium 1+ to measure viscosity. That provides a closed system which minimizes evaporation of the samples, which in this case that we have ethanol in our samples, this feature allows us to collect accurate viscosity data. Well, with that in mind, let's take a look at the relative viscosity data and melting temperature of 6 mg per ml DNA samples in the presence of ethanol. It is clear from the plot in the left that the viscosity decreases with increasing concentration of ethanol. As seen, there is a sharp increase in viscosity data that occurs between around 50 to 60 degrees C for all samples, which is because of DNA melting or denaturation. Again, we use sigmoidal feeds to determine the melting temperature. The plot in the right shows melting temperature as a function of concentration of ethanol. Unlike the spermine samples, here with increasing concentration of ethanol, the melting temperature decreases and shifts to lower temperatures. For example, for the sample without ethanol, it is around 59 degrees C. However, for the sample in 15% ethanol, the melting temperature drops to around, say, 52 degrees C. The major response of the DNA to ethanol is some form of internal compaction or condensation, and it's been reported in the literature that DNA is collapsed in the form of in a form of a coiled fiber with introducing ethanol. So depending on the type of the excipients you use, for example, here we examined spermine and ethanol, different structural changes may occur in DNA molecules. So just to quickly summarize this presentation before we go over the questions, I just want to highlight that we showed how we used the Vrock initium 1+ and viscosity measurements to explore the effect of different types of excipients on the viscosity and rheological properties of biological molecules, such as proteins and DNA. It allows us to perform temperature sweep experiments with high accuracy and reliability using a small volume of sample, which is an ideal feature since we are dealing with biological samples. We used different types of salts and amino acids as excipients that were added to proteins, and espermine and ethanol for DNA samples to see how they change the structure and rheological properties of these biological molecules. We showed that adding excipients into proteins and DNA samples leads to a reduction in viscosity in DNA that leads to structural changes, and that is called condensation. Also, we showed that increasing the concentration of espermine increases the melting temperature and reduces the viscosity. However, increasing the concentration of ethanol decreases melting temperature. So with that, we will go over to the question section and see if you have any questions.
Okay, so it looks like we do have questions, so thank you. So we'll start going over those now. Okay, so the first question is, could we provide some thoughts on solution viscosity versus ionic strength at a pH lower than the protein isoelectric point? So in this case, the data we shared earlier, we were above the isoelectric point, so we were looking at something that was negative or negatively charged or anionic. We actually have collected some data on the BGG or the gamma globulin where we did do below the isoelectric point. And of course, as you know, when you go below, now you're moving to something that's cationic. So we do see, I think I'd have to kind of pull up that data. I think that we have similar behavior in terms of the salt seems to have multiple effects, not just the hydration, but also screening the charges. So I think it is kind of similar to as when you move higher than the isoelectric point. But I think I'd rather not commit to too much beyond that because it's been a while since I've looked at that data. But you can definitely do those experiments as we kind of described, the ones where we went above. Okay, the next one. Do you perform any specific molecular modeling? Do you see correlation with experimental work, and can you recommend any modeling strategies? So unfortunately, internally, we don't have the capability to do molecular modeling. I do know of groups that we've collaborated with in the past, mainly at University of Texas at Austin, that have published some simulation results in addition to some viscosity data that they collected on either a couple of our different units. But yeah, I'd sort of direct you towards that group at the UT Austin. I'm trying to remember the professor's name, but it's escaping me at the moment. Hopefully I'll remember it before we end here as we go through the other questions. Yeah, but yeah, unfortunately I don't have, oh, someone just helped me out here. Keith Johnson, yeah. And I think there's other collaborators there as well that work on that. Okay. So let's see. Okay, so someone's asking about how sugars, things commonly used like sucrose and trehalose, and also some other oligosaccharides and cyclodextrins, how they would affect viscosity for proteins and antibodies. So our experience with those is that they tend to just increase the viscosity, mainly because you're increasing the background viscosity. So we didn't see any sort of initial drop in viscosity with the introductions of the sugars like we do with the salts or like we do with the amino acids or functional groups, they tend to just bump up the viscosity, mainly because you're bumping up the background viscosity of the solution. I think in general, the goal with those is perhaps more to improve freeze thaw stability, so cryostability. So necessarily reducing viscosity isn't necessarily the main goal. And so that's been kind of our experience, is that they don't tend to drop the viscosity, but rather increase it. Okay, so then we have a question is, what is a good viscosity range for antibody drugs? So that entirely depends on the delivery method. So, our experience is that with our customers have shared a variety of, sort of threshold viscosity values depending on the delivery method. Some people suggest that they don't want to go things above something like 15 centipoise. Other people are more okay going up to maybe like 40 to 50 centipoise. And I think the main difference is, the delivery method that they intend to use. And by that, I mean, what is the needle gauge, which then influences the inner radius of the needle, and then also what is the flow rate or delivery rate of the product. So those are the two main factors that are going to increase your injection force for a given viscosity. So, I would say, based on, our interaction with customers and what I've seen in the literature, it's going to depend, as I said, heavily on your delivery mechanism, but probably somewhere between 15 to 40 tends to be desirable for most people. So we'll pause here for a moment and see if we have additional questions, while we're waiting to see if anything else comes up. Anyone who signed up for the webinar will get a link to the recording, and then also will receive the actual slides that we shared. So if you want to review it again, and then also if you have additional questions, or if perhaps we didn't quite answer your questions as you had hoped, you can certainly contact us in the future, and we'll get back to you when we can. Okay, so we have a couple more questions that came in. One of these was, for the histidine and arginine experiments, was the pH adjusted to the same final pH? So in this instance, no. So there was an influence of not only the presence of the molecule, but how did that molecule impact the pH? So it was not. The other question that came in was, did we screen higher concentrations of spermine? The concentrations that we used were relatively low. Do we expect to see a continued decreasing in viscosity at higher millimolar spermine concentrations?
Actually, the highest concentration that we examine in these experiments is 300 microgram per mil spermine. However, based on literature, if you increase the concentration of spermine, it leads to precipitation of DNA. But we haven't seen in our samples because I think we haven't reached that threshold, that concentration that leads to precipitation. But yeah, we would expect to have precipitation of DNA at higher concentrations of spermine.
Okay, and then we have another question that came in. This is a general question. Do we think there will be any difference if measuring the viscosity is done by closed or open system pressure effect? So I think the only impact of the closed system versus an open system would be the fact that and maybe I'm misunderstanding the question. So if I'm not getting this right, please come back and I'll try to clarify. But I'm not sure what you mean by pressure effect. But I think in terms of open versus closed, you know, if you're referring to perhaps a different type of tool where you have an interface, then of course the interface can impact for evaporation or, you know, concentration gradients that can exist due to migration to the interface. But we don't see an issue in terms of, okay, so you're clarifying with or without pressure. Okay, so the clarification with or without pressure under atmospheric pressure or higher pressure. So we do measurements in multiple instruments. We have our automatic system, which is we refer to as a closed system, and then we have our manual system, which has basically the flow goes out to waste, so the exit stream is open. So the exit stream is at atmospheric pressure, and so we don't see differences in the measurements between the two units, whether the waste stream is, you know, going out to the open atmospheric or whether it's in this contained system. So we don't see any issues there with respect to pressure. Okay. So then we have one final question, or maybe not final, but we have another one. If we could design an excipient for protein viscosity, what would it look like? Well, I think ideally, you know, this is just my opinion, we would want to try to do something that would perhaps control the hydrophobic interactions that lead to attractions, but not minimize the electrostatic repulsion so much. And I guess I'm thinking about that in terms of kind of combining benefits of, you know, not only reducing viscosity to a certain extent, but not reducing that barrier so that you introduced instability. So that's my personal opinion. Others, I think, would suggest that the individual amino acids that we looked at are exceptional as viscosity reducing agents because they think that they do both. They both minimize attractions and minimize the repulsion. But I guess my concern is that if you minimize that repulsion too much, then you start to compromise on the stability, because that repulsion does benefit you in that manner. But I'm sure that you could get a different opinion from some others. So I think those are all the questions, and we are at the 1 hour mark. So I think it would be appropriate to end it there. So thank you so much for joining us today and all of the questions that you had. And again, if you think of things after you receive the recording and the slide presentation, please reach out to us and we're happy to communicate with you further. And then also I'd like to say that we will be having a December webinar, but it'll be more of a relaxed, fun type version. So if you're interested in that, please join us in December. We'll probably start announcing that sometime after this one concludes. So thanks again, and have a good day.
Thank you.